fun stuff to talk about Legos.
True.
When we get to group theory stuff, we could talk about Rubik's Cubes. So
I love Rubik's Cube.
Me too.
I'm obsessed.
I bought like 20 last year.
I have a collection.
So do
Oh,
I.
that's
I have
awesome.
like all the different.
Oh my gosh, should I bring them in?
So what you're saying is we need to spend a day and talk about solving Rubik's Cube using algebra.
I used to.
Yes.
I used to be able to get it
Okay.
in 48 seconds.
Holy crap!
Yeah. That was my New Year's resolution in 2022 to learn a Rubik's Cube, and by the end of the day, I could do it.
Oh, cool.
Because I was determined.
When I learn to do Rubik's Cube, I mix it up, and I can't leave it mixed up, so I have to finish it. Like, I'll watch a YouTube video until I finish it.
I can't do that fast anymore. I'd have to practice a lot. But like I used to be
I have
so
all my
fast.
room.
So
All my
fast.
bags are in my room.
That's hilarious. I love it.
I have not.
Yeah. Well, I think that sounds like a good algebra project. Then this
That would be so
That would
fun.
tell me anything else.
I would love that.
cool. No?
Oh my god, my senior
I mean, I
project.
saw one.
Yeah,
there
you
was
could.
no algorithm.
No,
there was
actually-
no knowledge behind it.
Wait
It was
a
just me fiddling.
second.
Fiddling until you did it? Yeah. Cool.
Took days.
Well, no, I think.
Not bad minutes.
Well, it plans at least one lecture later in the semester. So, cool. Sounds like fun. All right. I've never solved one, so it'd be fun to learn it myself. I know there's algebra behind it, so we'll talk about it. Cool.
Oh my god,
All right.
my senior project's gonna be on Rubik's Cubes.
What's that?
Like a
I
fidget
said my
toy.
senior project's gonna be on Rubik's Cubes.
That sounds like a plan. Might as well.
It's the only idea I've gotten so far.
This is
I
the
want
one
to
that
this out
Steve.
because I don't know if it's math enough. I wanted to. So I went to last year the capstone of Shay.
Yeah.
Who did a database around the world.
Yep.
But I wanted to kind of focus in on the part that I felt was missing from that one and build on top of that kind of a character generator.
Yeah, okay.
Because, or a variable character generator where you could input the specifications of your world. Because I just like add that piece, and if that's not a capstone, I'm still going to do it because I want to do it. But it is an idea.
Yeah, well, Dr. Roth should have her project, so you could absolutely do that. You need to do the math side of things, so I'd figure out how the math part works. But yeah.
Okay.
Yeah, that's perfectly acceptable ideas. Cool. We have questions about anything? My voice squeaks apparently. Is everyone okay? Yeah.
I'll come to your office if I go through these problems tonight.
Yeah. Okay. That sounds like a plan. All right. So last time, I think we ended up with subrings, right? Wasn't that the last time thing we were talking about?
Yeah, we did this.
Okay. So let's see if we can do a couple of examples with that. What I want to do. I told you to turn that one in. Let's look at number 12. Oh, I'm still in red from yesterday. It refuses to change to my other color pens. Oh, it's because it wants to kill it. There we go. That was fun. There we go. Page 55. Well, 54, whatever. It's the homework after section 3.1. Oh my goodness, why are you being a pain today? So we're going to use this notation. So it's a notation that we're going to use later as well. So when we have the set that's in front, that's telling us where the coefficients come from. And then when we use the brackets, inside that typically refers to a variable. So if I wanted polynomials with integer coefficients, I would write z bracket x. In this case, though, I really do want the complex number I. So if you think about polynomials in I, well, we know that I squared is equal to -1. So really, when you have a polynomial in I, as a constant term and an I term, that's all you get. Because the higher powers of I can be written in either as a constant or as an I to the first power. So this ends up being the set of all A plus BI, such that A and B are integers. We actually refer to these as the Gaussian integers. I don't think your book mentions that, but that's what these are called. Pardon me. We want to show that the Gaussian integers is a subring of the set of all complex numbers. Pardon me. So the complex numbers are actually a field. We've talked about field before, right? Field is when everything has a multiplicative, every non-zero element has a multiplicative inverse. Bless you.
Oh, thank you.
Yeah. Also has to be commutative as well. But it's a commutative ring with identity in which every non-zero element has a multiplicative inverse. That's what we mean by a field. If you eliminate the commutative and make it non-commutative, then you get what's referred to as a division ring. We're not going to play too much with division rings. Usually when we talk about everything having a multiplicative inverse, we're going to have a commutative ring. But just making sure that you're aware of the fact that division rings exist more than anything. All right, so subring, again, remember it has to be what? There's 4 conditions that had to be satisfied. Yep.
And identity and additive inverse.
Good. Yeah. So it has to be closed under addition, closed under multiplication, have the additive identity, and have every additive identity's inverse in there. Right. Mainly, you're looking because you know that if you're using the exact same operation that you do from the bigger ring, you don't need to worry about checking associativity of addition and multiplication. You don't have to worry about commutativity of addition. Pardon me. You don't have to worry about distributivity of multiplication over addition because you already have all of those for free from the bigger ring. If it is true for the bigger ring, it's true for the smaller ring, right? So you just have to worry about the ring axioms to make sure that they land back in the smaller ring. So the issues that you might have are your addition's not closed, your multiplication's not closed, maybe your additive identity didn't make it in there, or maybe additive inverses didn't make it in there. So to give you a specific example of that, if I look at the positive integers as a subset of the set of integers, well, positive integers would not have the additive identity. It wouldn't necessarily have inverses either, right? You could say, okay, I want the non-negative integers. Well, that's okay. Then you get the additive identity, but you don't get their inverses anymore under addition. Okay. So that's why we need to worry about those extra 2 conditions. The closure stuff makes sense, right? You did that back in subspace stuff, back in linear algebra with vector spaces, right? Wanted to make sure that the subspace was closed under those operations. We just have those extra pieces here to make sure that I could use the same additive identity and make sure that additive identity really is in there. And then same thing with inverses. So certainly, hopefully, we know how to do addition and multiplication in here. So if I want to take an A plus BI and add a C plus DI, what do I end up with if I rewrite it? Because again, I need to make sure it matches this form, right, to show that it's closed under addition. So how would we rewrite it to show that it matches that form?
A plus C plus B plus DI.
Good. And why is that back in the Gaussian integers again? What are we assuming about A, B, C, and D? They're integers, and when we add integers, they're integers again, right? So I'm not writing down a lot of the details here, but that shows our closure, right? Since A, B, C, and D are all integers, A plus C is an integer, B plus D is an integer, so the thing is back in there again. I wanted to put in all the details. What do you get when you multiply these 2 things together?
AC minus ED plus AD plus BCI.
right? I agree. Blush.
Oh, thank you. Just one second.
So the AD minus the B, excuse me, try that again. The AC minus the BD comes from the fact when you do the BI times the DI, you get BDI squared, or BDIs. Sorry. I thought it was funny. Anyway, I squared is -1. So you get the AC minus the BD. You can always depend on me for a bad joke, right?
It is in the syllabus.
You're exactly right. It's the syllabus. And the syllabus is a contract between the faculty member and the student. So I have to deliver. I have to make sure I deliver on that. All right. And then again, everything here is an integer. So when we do those operations, we get integers back again. Okay. So that was the first two axioms that we verified. We also need to make sure that the additive identity and additive inverses are in there. But what is the additive identity of the complexes? Not a trick question. What is the additive identity? What number serves as the additive identity? 0. Yeah. 0 plus 0i, right? 0 works, yes? Is 0 plus 0i in the Gaussian integers? Yeah, because 0 is an integer, right? So, good. So, if I write it this way, remember our notation for the additive identity is 0, and then if we want to be emphasis that we want it where the ring it comes from, we use that as a subscript. So the additive identity for the complexes, if we want to be really super hyper technical, remember complex numbers are written in the form a plus bi, or a and b are real numbers. So I could write it as 0 plus 0i, and that certainly is back in the Gaussian integers because 0 is an integer. What is the additive identity? Excuse me, try that again. What is the additive inverse of a plus bi? Just making sure we fit the right form for what needs to be back in the Gaussian integers again.
Negative I minus bi.
Yeah, exactly. Negative a, and I'll be even more pedantic about it. I'll write it as plus negative b times I, right? And if a is an integer, the opposite of a is an integer, and if b is an integer, the opposite of b is an integer. So it fits the right form, and that's back in the Gaussian integers again. So we really do get a subring. We're going to extend on this idea of subring later on in a few weeks, where we'll have an extra quality we would like something to have, where it doesn't necessarily, it's not just closed under multiplication, but it was what we refer to as absorbs multiplication. What I mean by that is we know that the even integers is a subring of the integers, but it also absorbs multiplication from any element in the integers, right? If I do 3 times an even integer, I get an even integer, right? If I do 7 times an even integer, I get an even integer, right? So it's even better than just being closed under multiplication. It absorbs all multiplications from anything in the ring to anything in the subring. We refer to that as an ideal, and we'll talk about ideals later on. So it gets a little bit extra, an extra quality. This is not an ideal because it does not absorb multiplication from anything in the complex numbers. So for example, square root of 2 would be in the complex numbers. It would be square root of 2 plus 0i. If I multiply an integer times square root of 2, I don't get an integer back again. So it would not absorb that multiplication. Okay, so this is not an ideal. Like I said, we'll talk more about ideals later. One of the other concepts they do talk about in this particular section is the idea of a subfield, meaning it's a field contained inside of another field. So I think I mentioned this briefly on Tuesday, but the rationals would be a subfield of the reals. all that means is that if I take the rationals, every non-zero rational has a multiplicative inverse that's also rational. So it's a field itself. That's a field contained inside the field of real numbers, because every non-zero real number has a multiplicative inverse. That's also a real number. And then every the reals is a subfield of the complexes, because every real, I just mentioned that a real is itself a field, and the complexes are also a field. So we have that going up property there of being a field contained within another field contained within another field. So we have the idea of subfields. This is not a field, because again, to do an inverse of a complex number, if you want the multiplicative inverse of a complex number, remember, if I think of it this way, we have to multiply by the conjugate to get the I out of the denominator. And you would have a minus bi over a squared plus b squared, which can be written as a over a squared plus b squared minus b over a squared plus b squared I. And certainly, if a and b are integers, there's no reason to expect that these fractions would be integers. Right. So it's not going to have multiplicative inverses. So it's a subring. It's not an ideal, and it's not a field. And the only reason why I'm mentioning, or it's not a subfield. The only reason why I'm mentioning these things is because that we're going to play around with these definitions more as we go build up more definitions. So I want to make sure I mention these things as we go along. Up until that last little excursion, the process of showing that it's a subring, okay, that would be expected to do on the exam. Those first 4 steps that we did. Okay. Pardon me. Let's make sure I don't do something I ask you to turn in.
No, please.
No, you want to go ahead and do something that we can. I did ask for 32. Okay, let's look at number 32. And then we'll start looking at some properties of rings. This is on page 57. They use a notation in the book for this. I'm not going to use the same notation because that notation they use is used for something else. The center of a ring is the set of all elements in the ring such that it commutes with everything else in the ring. It just disappeared. Did you see that?
Oh.
I didn't even touch it. It just went away. Like, nope, that R goes away. So it's the set of everything in the ring that commutes with everything else in the ring. That's what we mean by the center. The book uses the notation Z of R. That's what they basically extended the notation for what is used for groups. But Z of R means typically something else in ring theory. It means the set of zero divisors. At least in my research, it means a set of zero divisors. So I'm not going to use the Z of R notation for the center, because otherwise I got the exact same notation meaning 2 different things. So we want to show, this one asks to show that the center, why is this being such pain today? Not responding again. Okay. There we go. Show that the center is a subring. So again, we have 4 things to show. You need to show that's closed under addition, closed under multiplication. The additive identity is in there, and inverses are in there. Additive inverses are in there, right? I think the easiest thing to show first is that the additive identity is in there. Although we haven't proved this yet, if I want to show that the additive identity is in the center, let me give it a name just so that I can refer to it. I'll call it C. So I don't have to keep writing the center every single time. Okay. So let me give it a name. Don't scroll. Yeah, exactly what I want you to do is not move. Why are you being such pain? I love it. It's only in here that it does it. I don't have any of these issues when I teach my other 3 classes Monday, Wednesday, Friday. We come in here on Tuesday, Thursday, I have issues. I mean, I have issues, but I'm talking about with the computer. All right. So let's show that the additive identity is in the center, is in C. So again, to be in the center, it has to commute with everything from R, right? Well, why do I know that for every R in R, why do I know that 0R equals R times 0? What does that equal? 0. Yeah, I know that 0 times anything is 0. We haven't proved that yet, but the proof of that is the exact same proof that we did in linear. Remember how we proved it in linear? How did you rewrite 0? 0 plus 0 and then distributed and subtracted, right? So the proof is exactly the same proof that we did in linear. It's not any different at all, okay? But this shows that 0 commutes with every single element in R, which is exactly what it means to be in the center, okay? So 0 is in C. All right, so let's see if we can, basically, the reason why I wanted to do this, not only do we need to show that the 0 has to be in C, but before I start talking about doing things like closure, remember to be able to do things like closure, I have to start with 2 elements in the set. Well, the only way I can start with 2 elements in the set is if I'm sure that the set's not empty. So this also gives me a non-empty set to start with, so I can start pulling things out of it. Does that make sense? That was one of the things we had to do in linear as well, right? When we were talking about subspaces, I needed a non-empty set to talk about being closed under addition and scalar multiplication. Same idea. Okay. All right, so let's do closure under addition. So let's let A and B be in C, and we need to show that A plus B is back in C again. This is looking up at the screen now, and this gives me a little bit of a funny story from one of the times I taught abstract algebra, 15 years ago probably. So I wrote let on the board going on. All of a sudden somebody raises their hand and says, yeah, I go, yeah, whatever. They go, what's 6 plus? Look at my let. Like, that says let. That doesn't say 6 plus.
That's trippy. I didn't even see that.
Yeah.
Yeah.
But
No.
now
You
I
just
have to be
know.
able to
Yeah, you just know it's let. Exactly. So, anyway, I thought that was a funny story. But what's 6 plus? That was the second time I taught abstract algebra here. The first time was the story that I told you when somebody threw a bottle at me. I told you that story, right?
Yes.
Yes. So.
You're better than me. I'd walk out. I'd be like, this is not worth it.
Oh, I thought it was hilarious. I thought it was hilarious. I mean, I told her to do it, so she did. That's funny. All right, I need to show that it's in C. So again, we need to show it commutes with everything, right? And when I say commutes with, I mean under multiplication, right? So start with any element in R. It really does not like me writing the letter R today. It keeps erasing it. I had to write it twice again. All right. So let's do R plus AB. I need to get down to what? we're going to show it commutes with R, I need to get down to what at the end?
A plus B times R.
Yeah, but you get to A plus B times R, right? So how do you think we're going to get there? What do you think we need to do first? Distribute, yep. And then what are we assuming about A and B?
That they're in the center.
And they're in the center, so since they're in the center, how can we write RA and RB?
AR and BR.
Yep, AR and BR. And then finally, last step.
Steal that R away.
Yep, steal the R aways, and it's just in this case it's on the other side, right? Remember that for rings, we not only have left distributivity, but we also have right distributivity for that exact reason that we may have a non-commutative ring. And again, what did I tell you to think of when you want to think of a prototypical example of a non-commutative ring? What did I tell you to think about? What matrices? Yeah, we know that matrix multiplication in general is not commutative. Yeah. So if you want a prototypical example of a non-commutative ring, think matrices. So far, so good. Okay. So let's do, what else do we need? That was closure under addition. We need closure under multiplication, right? So if I do R times AB, we need to get down to AB times R. I got to do it a step at a time. What do I need to do first?
R times A.
Good. Yeah, got to reassociate. And then we can
Flip the R and the A.
good. Yep. Flip A and R. Got to do it a step at a time. Then what do we do?
The parentheses are R and B.
Good.
And then
Flip them and reassociate one more time. So in the first case, I should have put a conclusion statement, right? In the first case, we would have A plus B is in C. And in the second case, we have AB is in C.
Like that tower stacking game. Where you have the rings of various sizes, you can only put the smaller ones on top of the larger.
Oh, well, the Tower of Hanoi.
Yes.
Yes, we have one of those in the suite. Actually, I think we have one in the suite and one in Dr. Rolf's office. The one that's in the suite has the rectangular boxes on them, but they're not very nice because they don't sit where they should. Because the boxes are, so you got the 3 poles, right?
Yeah.
Well, the rectangles are so big, you can't set one this way, and then the other one doesn't sit right on if you try to move it. So you have to put them long ways. But Dr. Ross got one nice one with discs instead of fun to play with. You know what we're talking? Others know what we're talking about with the Tower of Hanoi.
I think Dr. Rock brought it to class.
Yeah.
I don't know what class that was, but
No idea. Oh, so
It might have been theory.
so the idea is that you've got 3 posts, and on one of them you've got discs of decreasing size stacked up. And the idea is to move the tower exactly as it is to another pole by only moving one disc at a time and never putting a bigger disc on top of a smaller disc.
Oh.
So I can move, say, this one here, and then I can move that one over here, and then move that one over, and then I can move that one over that way. And then take the little one, put it here, take that one, put it there, and that one there, and now I've got 3 on that one, and you can keep going. It's an example of recursion, because once you solved a smaller one, you can solve a bigger one, and solve a bigger one, and solve a bigger one. So that's what Tower of Hanoi is. What's that?
Fascinating.
I don't believe you. It is a cool little light, but there are some interesting things with kind of the recursive process. I remember as an undergraduate going to an undergraduate math conference over at Rose Holman and Terre Haute, and they were talking about these codes, and then they had this little game that was there to had all the pegs on the inside, and you had to move them all to the outside. It was following those codes that the guy was talking about in the lecture, so I played with that for a long time after his talk. All right, anyway, last thing we need to show that it's closed under additive inverses, right? So if I talk about, I need to do r times negative a, and I need to get to negative a times r, right? So one of the things that we would need to show, because we haven't done this yet, because we haven't done the properties of rings, but the proofs of the properties of rings work the same way as they did for the linear algebra stuff that we did. So just to do this off to the side, one of the properties that we had in linear for vectors was this one. Remember that one? Where I can move the negative wherever I wanted to. I can put it on the first one, I can put it on the second one, I can put it out in front. And the proof is basically the same. This part here, it says we have the additive inverse of AB, and so we want to show that each of those behaves like it's the additive inverse of AB. So I would take AB and add the negative A times B. And I want to show that I really do get 0. What can I do with the B here? I can pull it out to the back, right? Because again, ring multiplication is left and right distributive. So I can pull the B out to the right. Can't pull it out to the left because I don't know it commutes, right? But I can pull it out to the right. And then A plus negative A is 0, and 0 times anything is 0, because that proof is the same as what we did in linear. We talked about that a little bit ago. It's the same proof. Okay. So in any event, that this tells us if I just then add your AB inverse to both sides, I get that negative A times B is the same thing as the additive inverse of AB. And it's the same proof for A times negative B. I would just pull the A out on the left rather than the B out on the right. Literally the same proof. What we do not want to write here for rings in general is negative 1 times B. I can, if I have a multiplicative identity, I have a 1, I could do it that way. But generally speaking, I can't write negative 1 necessarily. If I have a ring without identity, like the even integers, that's a ring without identity. Right? So I can't write negative 1 because negative 1 doesn't exist in that ring. Okay. So I don't want to write negative 1 times something necessarily. Okay. All right. But in any event, we go back over to our center idea. We can pull the negative out. Once we pull the negative out, what can I do inside the parentheses? Yeah, rearrange them, right? And then I can put the negative with the A. Notice to show that it's in the center again, it's a multi-step process because I got to break it down to the element that's actually in the center that I can deal with, right? In the first couple of examples, we had an A and a B. I had to work with the A and the B individually. Here I've got a negative and an A, but I still need to get down to that A individually to be able to flip it. So in any event, negative A is back in C again. So we've satisfied all 4 properties of being a subring. Hence, C is a subring of R. Unlike later on this semester when we'll talk about subgroups, there is no good notation for subring. Just write it out. least there's no accepted notation for subring. You just write out the word subring. Is this okay?
You just gotta keep referring it as something until other people start doing it.
There you go.
Brute force your way into acceptance.
All right. One last problem. I'm not going to do this now. I'm going to use it for practice. I want you to play around with number 43. This is on page 58. I don't want you to turn this one in. But this gives you another example of a ring that's not commutative, that has an identity. And if you've had history of math, you probably talked about the quaternions, the bridge that William Lowell Hamilton walked across and carved in multiplication. I squared equals j squared equals k squared equals ijk equals -1. Maybe you talked about that in history of math, maybe not. Anyway.
It sounded like you just recited like an ancient myth.
Does it? Yeah.
Or maybe
I just summoned some demon from the 8th dimension or something.
Maybe it was more so like Lord of the Rings, like Aragorn, son of God, walked across this bridge.
William Lowell Hamilton. Hamiltonian graphs. Did you talk about Hamiltonian graphs in discrete? No? Because you had me for discrete, so it's probably too much with Hamiltonian graphs. Anyway, same person, Hamilton. William, not Alexander Hamilton, but...
There's only one Hamilton.
Oh, I'm sorry. I said Lowell. It's William Rowan Hamilton. Sorry, I almost said his middle name incorrectly.
We would have never known.
You might go look it up. You never know.
You could lie to us. We would never know.
I would have never known because I did not give.
We didn't have spirits when we were margins of the Federalist
No filter.
That's all right. No filter. No filter is perfectly fine with me. I'm perfectly happy with that. Anyway, you can actually go to the bridge in England where he carved that stuff in, but he was working on a problem. That's where the quaternions came from. So, in any event. Oh, Laney doesn't think it's interesting. Clearly. All right. Let's talk about some basic properties of rings, which we've already talked a little bit about them. All right. So basically what they're trying to do in this particular section is we've already talked about how these properties work in the integers. We've talked about how these properties work in the Z mod n type rings. So they're just going along and making sure that you understand how these properties work in rings in general. And we've already alluded to some of these anyway. So just to write down some of these that are in here and not necessarily go through the proofs. In R, the equation a plus x equals 0 has a unique solution. This is just a fancy way to say that additive inverses are unique.
Their mother told them they were special.
You're a good little solution. All right, so remember in math, we already know that there has to be a solution based on the axiom, right? Every element has to have an additive inverse and additive inverse. It's not English class, I suppose my grammar doesn't have to be great. Has to have an additive inverse, right? Remember, if we're showing uniqueness, we would assume that we have two and show that they're equal, right? If you have, say, a plus x equals a plus y, well, we already know that I could add either x or y to both sides. Doesn't matter. It'll kill off the a, right? So let's say we add x to both sides just for argument's sake. This is the long way to get at it, but that's okay. That's okay. That's all right. I'll rearrange here. So we're saying that they're both additive inverses. If they're both additive inverses equal to 0, they're both equal to each other. Add x or y, doesn't matter which one, to both sides. Reassociate, but again, we're saying that x is an additive inverse for a, so x plus a has to be 0. And then it's the additive identity, so x has to equal y. So you only get one solution here.
I was trying to think, because we usually prove existence and then uniqueness. Is there a spot where there's uniqueness but non-existence? And my first thought was like roots of polynomials when you're not including complex numbers. Like when I can appear, but it technically doesn't exist in that set.
In that particular one, yeah. So in that case, it's a good question. So the short answer is no, because we had the basic way we showed is we assume we have 2. So if there doesn't exist any, then it can't be unique. It's a good philosophical question, I suppose. There's exactly one thing that doesn't exist. I would say the short answer is no.
I said it was an answer to that question.
Okay, so anyway, that's that theorem 3.3 basically just says that additive inverses are unique. I'm not going to go, I mean, you can do the same, which is why we use the opposite of the element to denote the inverse for the additive inverse. Theorem 3.4 basically says we have cancellation. This is a property we'll come back to when we talk about groups in general. But again, the proof here would be to add the inverse of A to both sides, reassociate, get 0, and show the B. We'll see it's basically the same proof that we have above. The whole reason why they're doing this isn't necessarily because it's a very interesting result, because it's not in and of itself. The reason why we're doing this is because we have cancellation under addition, but we don't necessarily get cancellation under multiplication. Okay? Cancellation under multiplication is a special property of being in an integral domain. That's where we get cancellation under multiplication. Okay? To give an example of not being able to cancel in multiplication, in Z mod 6, 2 times 3 and 4 times 3 are the same thing. It's 0, right? Yeah. Okay. But 2 and 4 are not the same thing in Z6. So I can't cancel multiplicatively there. That's the reason why they're trying to make the distinction between these things. You can cancel additively in any ring, but generally speaking, in a ring, you cannot cancel multiplicatively. So again, like I said, that particular result's not surprising at all because you have additive inverses, right? So you just subtract A from both sides, which is what you've done since you started learning algebra, whatever year that might have been. For me, that was 4th grade because they didn't know what to do with me. So I said, here's an algebra book. For those of you who are going on in education, I implore you, don't do what they did to me in grade school. Oh, you're really, really good at this, so we're just going to send you out in the hallway with extra work. So I was completely separated from the rest of the group for math for, 5 years. Don't do that. It's a bad way to deal with a kid who's either way, either gifted or struggling. Don't do that. That's just a side note. But in any event, all right. But do we understand why I'm making a big deal out of this with the cancellation? Because we can't necessarily do it with multiplication. It's a special property. cancellation under multiplication is a variant of that zero factor property idea. All right. So other properties, and these properties are just exactly like what we talked about in linear. So I'm not going to go through the proofs because the proofs are the exact same proofs that we did in linear. So theorem 3.5 actually has 7 parts to it. The first one says that 0 times anything is 0, which is the same thing as a times 0. Remember, the trick for proving that is to rewrite 0 as 0 plus 0 and distribute. The second one is what we just proved a minute ago, or probably longer than just a minute ago. Maybe it was a couple of minutes ago. We can move the inverse to where we want to, either on the first thing in the product or the second thing in the product or outside of the product. If I want the additive inverse of the additive inverse of A, that's just A, which is just basically a restatement of the thing that I add to the additive inverse of A to get 0 is A. That's all that says, right? In words. The thing that I need to add to the additive inverse of A to get 0 is A, which is exactly what it needs to be an additive inverse, right? So not a very interesting property in and of itself. 4 says additive inverses basically distribute over sums. This is another idea of being that inverses are unique, which is what that theorem 3.3 mentioned. To show that this really is the additive inverse of A plus B, I would show that it behaves like the additive inverse of A plus B, right? So I would add it to A plus B. And show that I get 0. Well, what do we know about addition with respect to the individual pieces? It's commutative, right? So I can put the A with the negative A and put the B with the negative B. Technically, there's some reassociating going along in there too, but since we know it's associative, I can just lose the grouping symbols. And now we get 0 plus 0, which gives us 0. This again is just using the fact that we're just showing that it's the additive inverse of A plus B. It behaves like it, so it has to be it because inverses are unique. 5 says the exact same thing as 4 does, except that it says that it's subtraction. Well, this is not a huge surprise because how do you define subtraction just generally? Subtraction is the adding the inverse, right? Okay, so the proof of 5 would be to rewrite A minus B as A plus a negative B. Use 4 to distribute your minus sign, and then 3 to simplify your minus and minus. So 5 is just 4 and 3 together. 6 says if you take the opposite of A and the opposite of B and multiply them, you get AB. This one, I can play with. There's several ways. A lot of these are several ways that you can get to the same answer. This one I can just play with previous properties that we've already done. What property did I use to rewrite that to make that statement? 3, right? And then what property did I just use to make that statement? 2. Put the negative sign with the second element. The end. That was the proof. 7 says if R has a multiplicative identity, we usually abbreviate that to just say R has identity or R is a ring with identity, because every single ring has to have an additive identity, no matter what the ring is. So it doesn't make sense to specify it has an identity to mean it has an additive identity. They all do. So just by saying R has identity means it has a multiplicative identity, because that makes it special, right? Not every ring has a multiplicative identity. So this says if R has identity, then -1 times A is the opposite of A. And we use 1 to mean the multiplicative identity, whatever that happens to be.
Hell of a theorem.
What's that?
So a hell of a theorem.
It is a hell of a theorem, isn't it? It's got 7 properties. I know. This one is just, again, it says that something is the additive inverse. So I would show that it behaves like the additive inverse by taking -1 times A. Oh yeah, don't scroll. By all means. I would take -1 times A and add it to A and show that I get 0. Well, the first thing I would do is rewrite A as 1 times A, and then what would we do? Yeah, pull out the A, maybe. There we go. And then -1 really means the additive inverse of the element 1. So -1 plus 1 is 0. And I really do get 0. That's general. When we have a result that says prove something is equal to the additive inverse of something, that's basically what we do, is we just show that it behaves like the additive inverse. We just add it to the thing that we're doing the inverse of and see that we get 0. That's pretty typical. And again, that's using uniqueness ideas. But like I mentioned, those look a lot like the linear algebra proofs we did last, whatever it was, just in the spring, wasn't it? Yeah, we just did do linear in the spring, didn't we? You know, we had you for linear. All right. Questions on that at all? So other things that they play with in this particular section is making sure that you understand common notations of things, making sure that you understand that not everything is commutative, so rewriting things may be a little bit more challenging if it's not commutative, and then giving some formal definitions for units and zero divisors. We've already talked about that a little bit. So let's just play around with different things. So we use exponents exactly like we would use exponents. Like you would expect. So we'll use that shorthand notation for factors. We also use, even if we are in a ring that it's not the integers, we still would use this notation to mean we've added A to itself n times. So you have to be a little bit careful. Even though that looks like multiplication, we may not really mean multiplication, depending on what the ring is. Now, it may turn out that it really does behave like that, but that notation literally means add A to itself n times. It does not necessarily mean take the number n and multiply it by some other arbitrarily defined element A, because that multiplication may not be defined. Okay. Now again, it may be the case that it behaves like you would want it to, right? What I mean by that is those are two different types of objects, right? So technically, according to what I'm saying here, this notation says add this matrix to itself n times, right? But it behaves then exactly like you would expect it to. I would just distribute the n to each of those pieces. Okay. But technically, that's not what that means. This means added to itself n times. It just ends up behaving like you would expect it to. Okay. You know, making a big deal out of it. And you're probably like, I don't care because I know Lainey doesn't. You started it. In any event, just be careful with that because that does not necessarily mean multiplication. It means added to itself that many times. Okay. All right. That's the whole point. So, making sure that we're all on the same page with that. Here's the prototypical example of what they mean that you need to be careful with things. So let's say we want to actually do a plus b squared. Okay. You're so used to writing this, right? Immediately just do that. Okay. Well, we have to be a little bit careful because this means do a plus b times a plus b. I have to use the distributive property twice. Let's take this thing and distribute on the left. So you'd have a plus b times a, and then a plus b times b, like that, right? Take that whole chunk a plus b and distribute it to those two terms. And then I have to do the distributivity property again, except now I have to use right distributivity, right? I got to come from the right side. What do you get for the first product when you do that? Plus BA, good. And for the second one? Good. Are these two things necessarily equal to each other? No, because the only way they are equal to each other is if those two things are the same, right? If AB is equal to BA. So these are only equal if the A and the B commute with each other. And even more so, if I know that a plus b squared is a squared plus 2ab plus b squared for any a and b that you choose, then you actually have to have a commutative ring. You actually have to know the multiplication commutes for every two elements. Okay. So this is one of those be careful things. Make sure that when you're doing the multiplication, you actually are doing it from the correct side. But the reason why I went through that notation stuff is because notice I used both notations when I did that. One thing I will mention as a curious aside. What if I'm talking about a ring here? I shut the doors. What if I'm talking about a ring here when I add something to it? What's that?
Can you hear them too?
I hear you. Oh, there's always voices running in my head. Oh, gosh. You don't want to be in here. One of my friends from grad school said, you have Calliope music playing in the background all the time, don't you? Pretty much. Yep. That's pretty much what's going on in there. All right, anyway, I lost my train of thought now that I was talking about that. Notice that we talked about Cartesian product things, right? So let's look at a quick example of just, if I look at this particular ring, this would be ordered tuples. Where does each of your coordinates come from? Be A, B, A, comma, B, comma, C, but what do your A, B, and C have to be? 1 or 0, yeah. So how many total elements would you get? How many choices do you have for the first component? 2. And for the second component? 2. And for the third component? 2. So how many total choices do you get? 8. You gotta multiply. You gotta multiply, right? 2 times 2 times 2. That's fine. It's fine. there are 6 and 2 more.
It's 6, so we're not wrong.
Yeah. You weren't too big. It wasn't too high. You gave me a lower bound on the number of elements. There is a cute video of making these 2 little girls are talking to each other about one's trying to teach the other one subtraction, but he keeps going and one more, but there's adults doing the voiceover of it. It just cracks me up. So when you said 6, I'm thinking and one more and one more. All right, so there are 8 elements in here, but each of them are 0 or 1, right? So in particular, if I take an A, B, C, and I add it to itself, no matter what the A, the B, and the C are, what do you get?
Or no. Or 2. Wait.
So it fits.
And one more. All right. What if I just take that? What if I don't worry about where I'm living, and I just want to add those 2 things together? What do you get? Yeah, that's okay. Say it. That's all right.
2
Yeah, 2A, 2B, 2C, right? I would get 2 A's, 2 B's, 2 C's. But what ring are we in each of those components? You get 0 all the time because 2A is 0, right? Because we're reducing mod 2. 2A is a multiple of 2. Reducing mod 2, you get 0, right? The remainder when I divide a multiple of 2 by 2 is 0, right? So this is always 0, 0, 0, no matter what, right? So if I add something to itself twice in this ring, I get 0, 0, 0 every single time, right? So in this particular ring, this is certainly commutative, right? Well, that made out. Okay. If you take A plus B squared in this case, what does it simplify to? This is commutative, so I can write it that way. What does it simplify to in this ring? It simplifies to A squared plus B squared. I probably should have used a different letter than A and B, but since I used them for the components up there. But in this particular ring, since 2AB is always 0, I get A squared plus B squared. What does it look like you did with the exponent? It looks like you just distributed the exponent, doesn't it? Right? Let's do another example. How many elements does that ring have? 9, right? Because you have 0, 1, and 2 for the first component, 0, 1, and 2 for the second component, and I don't add them, I multiply them. Yeah, I'm sure it's more than 6. Again, lower bound on it, that's good. Sometimes you want to bound things. There's lots of theorems in mathematics that talk about bounds of things. It's okay, you give me a lower bound. You can give me an upper bound. There's 15. That's a... We're not. All right, in any event, so there's 9 in here, but everything here, the components would come from 0, 1, and 2, right? So what if I asked you to do AB plus AB plus AB? What would you get? Oh, we get 0, 0 again, right? I get back to 0. No matter what your A and B are, right? Because when I add that together, I would get 3A, 3B. But 3 is 0, mod 3. Right? Okay. So now I ask you, in this ring, what would A plus B cubed equal? Well,
That's not actually.
no, it's not that bad. Do you remember Pascal's triangle?
We did it with the data.
The ones down the diagonals this way, and how do you get the ones in the middle here? Add the ones that are up above it. what do those give you? The coefficients on this is x plus y to the 0 power, x plus y to the first power, x plus y squared, cubed, and so on, right? It gives you the coefficients on what the expansion will be in those, right? It's an application of the binomial theorem. In any event, what does this become?
A to the third plus b to the third,
Eventually, yeah. So we get a cubed plus 3a squared b plus 3ab squared plus b cubed, right? Start with a cubed, make your powers of a go down by 1 each time, make your powers of b go up by 1 each time. That gives you the terms that you need. The coefficients follow those patterns, right? And notice that your middle terms cancel out again and you get a cubed plus b cubed. There is something special going on here because in these particular rings, we're able to just distribute the exponents. Okay? To give you another definition, the characteristic of a ring is the smallest positive integer smallest positive integer n such that not responding again because I can't scroll because I need more paper, virtual paper at least. Go. Not responding.
One day.
Sometime. Why are you not? Oh, there it responded. Such. It's a sign I'm about ready to frisbee this computer is what it's a sign of. There we go. Such that n times r is equal to 0 for all r in R. This is what we mean by the characteristic. It's the smallest positive integer so that I can take r and add it to itself n times and get 0 no matter what I pick for r. Now, obviously, at least I hope it's obvious, there may not necessarily exist a positive integer for that which that works. For example, if I take the integers and add 1 to itself over and over again, do I get back to 0? If I take just the positive integers and add 1 to itself over and over again, do I get back to 0? No. So, if no such positive integer exists, we say the ring has characteristic 0. Okay. So going back up to the previous two examples, that first one we did was Z2 cross Z2 cross Z2. We said when we added any element to itself, we got 0. So it would have characteristic 2. In Z3 cross Z3, we said that when we added any element to itself 3 times, we got 0, no matter what the element was. So Z3 cross Z3 has characteristic 3. Okay. In general, this is what, and we're not going to prove this because it requires more than what we have right now, but I do want to mention it because I think it has a funny name. This is what's referred to as the freshman's dream. If the notation for a characteristic of a ring is CHAR of R, if the characteristic of a ring is a prime power, then a plus b to the p to the n is a to the p to the n plus b to the p to the n. Now, of course, it's called freshman's dream because why? what do beginning algebra students want to do with that exponent? Distribute it. So that's why, like I said, it just gives it a funny name. I just wanted to mention what the funny name was. But the idea of characteristic is something that we'll come back to. Generally speaking, if you have an integral domain, your characteristic always has to be prime. Think about why. If your characteristic were composite, let's just say I had n times 1 gave me 0, where n is the smallest positive integer that works for. If n is composite, that is, let's say n is a times b, I could rewrite this way, and now I've got 2 non-zero things that give me 0. Okay. So characteristic is something that we'll come back to later. Okay. All right. We just didn't mention units and zero divisors, but we already talked about them a little bit. So let me give you a couple of problems to work on. Let's look at, not too many. Let's look at 8 and 11 and 12 on page 67. They are proving some things are subrings. On page 63, they give you a theorem that shortens your proof for showing something as a subring. In particular, you can cut it down to 2 pieces, like what we did for subspaces in linear. You can cut it down to 2. The 2 conditions are show that it's closed under subtraction and show that it's closed under multiplication. If you can show it's closed under subtraction, that takes care of the inverses part. You do need to worry about it being non-empty, so you'll have to show something is in there. But that's theorem 3.6 on 63. It gives you a kind of a subring test. All right. Have a good one.